Okay, hi everyone. Yeah. Are you able to see the screen? Okay. Can see It's
Yeah.
a black screen right? Okay. Okay. So, today the oh okay today we're gonna do quite some revision. Okay. So yeah. Okay. I think all's good now. So do take note that the video will be recorded. Okay. Yeah. But since none of you are switching on your cam, I think it's fine. Yeah. But yeah, if you want to ask question and you feel like you want to be muted, just let me know. I'll mute you in the video, right? Okay. Otherwise, yeah, today we are going to actually do on chapter 6 and 7 first. So that's part of the Newtonian mechanics, right? So that's like things that you can see, right? So these two the chapters will include pressure and work energy power, and then after this we'll be showing a short video which will bring us to chapter 8, 9, and 10, which is really just heat transfer, right? Thermophysics, right? And then after this, we actually go into chapter 11, 12, 13, and 14, which is like your wave, light, sound, and EM wave. Okay? And then if we have time, then we can actually go into the last part, which is electricity, right? So actually, yeah, I'm just banging on the fact that since we just finished the whole chapters on electricity, right? Yeah, you all will be able to remember most of it. Okay, so I want to do this revision first. Okay, so chapter 6 and 7, I think chapter 6 is quite straightforward. Okay, so let's start with chapter 6, pressure. Right, so the formula for pressure is equals equals to force over area. Now this area is your contact area and not your base area. Okay, so contact area is defined as the area that is touching the ground, right? So the object and the ground, how much they are in contact. Okay, and this force is the force applied. This is just a force, right? That the object is applying on, say, the ground, or the ground is applying on the object, depending which pressure you are trying to find, right? So this pressure. Okay, this area is always in meter square, and this is in Newton. Okay, unless the question specify otherwise. Otherwise, this is the standard unit. Okay, and in case you forgot already, 1 meter square is equal to 100 times 100 cm square. Okay, so just remember this square, right? So 1 meter is 1 meter, 1 meter, right? Another way to write 1 meter square is also, because 1 meter is equals to 100 cm, we know that this is also 1 meter square. And the area of this square is 100 cm times 100 cm, which actually gives us this value over here. Okay. Okay, so that's the idea. That's the idea of pressure, right? And then a very common question that they like to ask in pressure is that what happens if I increase the area, right? Or what happens when the weight of the person increases, right? Then what happens to the pressure? So the relationship, I think, is quite straightforward. So pressure increases when the force increases or when the area decreases. Of course, the opposite is true, right? So pressure decreases when force decreases or area increases. Alright, so we get this from our formula P equals to F over A. So very common question, they'll ask you what happens to the pressure acting on this surface or acting on a person when a very common question would be like a car, right? So like what happens if I change the tire of the car to a tire that has a larger contact area of the ground? Then the pressure will actually decrease, right? So we use the PRO method, the principal relation and outcome, right? So the principle is always this, P equals to F over A. Then you relate, right? So you relate using this, and then you give the outcome. Does the pressure increase or decrease? Right? Okay, so this is how you are going to explain certain questions. Okay, then the second part of pressure. Pressure is a short chapter, so we are about to end the revision on chapter already. Right, the second part on chapter. Does anyone need to copy this? By the way, if you think like you want to just focus on listening and not copy, it's fine too. I'm asking you all to copy because I think like otherwise I scare you all fall asleep because it's going to be a bit dry. Because at the end of the day I can still send you the PDF file. Okay, so it's fine if you are not copying. Okay, then the next part will be hydraulics, right? So let me just set a hydraulic system. Okay, not the best looking hydraulic system. Okay, so this is a hydraulic system. So let's say we have a force acting on the left piston, so we call this F1, and the area of the left piston is known as A1. Okay, and then I have A2 over here, the area of the second piston. Now if I push F1 downwards, right, then naturally the force acting on A2 will be upwards. Yeah, hope you all will be able to see that. And then in between them, right, is some kind of liquid. Okay, preferably oil, because oil has lesser resistance than water, right? Because oil is smooth, right? Water is not as smooth as oil, right? So by feeling, and we know that oil has lesser resistance. Okay, so preferably some kind of oil or grease over here to allow smooth transition, right? Okay, so when F1 acts on the plate A1, it actually creates a pressure, and this entire thing works, right? Okay, it's based on the principle of 100% pressure transmission. Okay, not force transmission. The force F1 and F2 will not be the same, but the pressure that is exerted on A1 and experienced by A2 will be the same. Okay, in other words, what I'm trying to say is that P1 is equal to P2, right? And with the help of some liquid over here, we can achieve this. Okay, because this is not compressible. Okay, now if there's gas over here, okay, so let's say there are air bubbles here, right? So instead of having all this, hold on. Instead of having all this as some kind of liquid, right? Okay, in the liquid itself there are some air bubbles. Now what will happen is that suddenly the liquid is not entirely incompressible, because as you compress and burst these air bubbles, right? So these air bubbles pose as an issue, because the air bubbles can be compressed. Now when they can be compressed, right, part of the pressure that is transmitted in this direction will end up being wasted, so that the pressure here and the pressure here will no longer be the same. Okay, so what we want is to have your liquid pure liquid and no air bubbles, right? Because when there's air bubbles, it can be compressed, and this idea of being able to be compressed, right, actually causes pressure to not be fully transmitted. Okay, so that's the idea of a hydraulic system. Okay, and of course the formula.
Water works here.
Huh? Water works here.
Water works here.
Yeah, but oil works better.
Okay.
Okay, so the formula goes P1 equal P2, which gives us F1 over A1 equals F2 over A2. Alright, so usually they will ask right, if the area of this piston is given, this force is given, and this area is given, now what is the maximum force limit that this hydraulic system can take. In other words, they are trying to ask you to find F2 lah, right? Okay, and since you are about to, so once I end this, you'll go to energy. Then I think I'll just start energy here, right? Because what happens is that it seems like when the A2 is bigger, F2 will be larger, which is good thing, because if you use a smaller force, it actually produces a larger force, right? However, the setback is about the distance move, right? So how much must I move? Okay, this distance 1 to move this up, okay, by a certain distance, right? So let me just draw this again. Okay, so if I want to achieve D2, right, how much is D1 going to be, right? So we know another thing that is 100% transmitted, which is energy, right? So since energy cannot be created or destroyed, only can be transferred, right? If there's no friction in between the walls, this will be 100% energy transmission, right? So assuming 100% efficiency, then the work done on piston 1 will be equal to the work done on piston 2. And recalling the formula for work done, which is force times distance, okay, we'll actually be able to get this formula. Okay, so F1 is pushing the piston 1 down a distance D1, which causes piston 2 to experience the force F2, which causes it to be pushed up by D2, right? Okay, so I'm just going to write here, this is upwards distance, while this is a downward distance. Okay, to make it clearer for you all to see. Alright, so that's the idea of pressure plus a bit of work done.
Will they ask us to calculate something like efficiency?
Yes, so I'm going to teach you efficiency the next chapter.
Okay.
Sorry, someone asked a question, but I don't understand your question. The pressure will not, when where will not be the same. Oh, okay. Oh, okay. So the pressure over, so by right, pressure everywhere should be the same, but with air bubbles, meaning the pressure transmission becomes 95%. And then with even more air bubbles, right, the transmission becomes 90%. Yeah, because air bubble can be compressed, so you are going to use a pressure for something else. You are using it to compress. Yeah, okay. Yeah, thanks for the concern. Yeah, I'm recording. Yeah, I'm not recording through Zoom, and the Zoom recording not very good. Yeah. Okay, so I think it was yeah, if you have problem with understanding what I mean by pressure transmission 100% or 90%, you can ask me later, right? Okay, so this is the pressure page. Anyone need me to stay here for a while to copy? If not, I'll move on to energy now. You can type to me privately on the Zoom chat, or you can voice out if you need. Okay, if not, I'll move ready. Okay, then we go to the next chapter, which is energy, right? So then we have power, right? So these are the two things that we are going to study, right? So let's look at energy first, right? Power should be quite familiar to you. In fact, you all just did power recently again, right? And it's quite similar formula. It's just that instead of potential or kinetic energy, you're dealing with electrical energy, right? So in this chapter, we are just going to look at a few types of energy. Firstly is namely your kinetic energy, right? And then your gravitational potential energy. So we are going to zoom into these two and look at it in more detail. Of course, other energy that you need to know includes things like your elastic potential energy or your chemical potential energy or your electrical potential energy, right? Which is the energy that you have been dealing with for a while in the past few chapters of our lessons, right? So we have elastic potential, chemical potential, electrical potential. Okay, however, we are not interested so much in these three today. We are more interested in this, right? Okay, so without further ado, right, so kinetic, I think everyone should be able to remember the formula. Please remember the formula. So k equals to half mv squared, right, where m is the mass and v is the velocity. And whenever we find change in ke, please don't end up finding a change in velocity. It's always the ke final minus ke initial, right, which will give us half mv final square minus half mv initial square. Okay, so that's how you find the change in ke. Now ke has to do with speed, so the faster the object, the faster the ke, right? And then we go to gp, which gives us the formula mgh. If you can recall, mg is also weight, so it's actually weight times height, right? So gp is caused by gravity, and hence the force here is weight. Yeah, so it's quite straightforward, because I mean, it's quite intuitive, not straightforward, sorry, because if gp is the energy given to you due to Earth's gravity, right, then the force acting on you must be because of gravity as well, and that force has a name, and the name of that force is actually weight. Okay, hence you actually, if you manipulate mgh a bit, getting wh is quite normal, it's quite alright. Yeah. Okay, another way to calculate energy is actually known as work done. Okay, so not all energy can be accounted as gp or ke. For example, the energy that I'm about to give an object, right, is neither ke or gp at that point of time. The energy that I give to the object can allow it to gain gp, can allow it to gain ke. Okay, but I wouldn't say that the energy that I'm giving to a box, right, when I'm about to touch it, right, can be categorized into either ke or gp. Okay, so work done is more like a general form of energy input or output. All right, so this is still energy, right? So work done is still energy, and it's a energy input or output, input or output by either an external factor or by the object itself, right? So if you don't know external factor, an example would mean like you pushing the box. So when you push a box, do you give it energy? You do lah, right? That's why it can move. Okay, but the object itself, right? So the energy can be lost by the object itself, and that is because of the friction, right? So it's actually the box moving against friction, so it's going to end up losing energy to friction.
So that is object one.
Object itself. Okay, and the formula for this work done is given by, we mentioned earlier at the hydraulic system part, right? So it's actually force times, so let me write nicely, work done equals to force times distance. Now this W here is weight, I don't want you to be confused, and this W here is work done. Okay, which is actually quite similar to this formula, right? So these two, because W is the force and H is the distance, right? Okay, so take note that this distance must be in the same direction as force. Alright, so yeah, that's about it. Okay, so the grand formula for this chapter, right, is actually here. I need you all to consider, right, the KE initial plus the GP initial plus the work done on object initial using the conservation of energy, right? Okay, we know that this will be equals to the KE final. If the object stop moving, right, KE final is just 0, right? If the object was not moving initially, right, KE initial is just 0, right? So just by reading the question carefully, a lot of this can become 0. Okay, if the object is moving along the same height at all times, then the GP initial and GP final is just 0 as well, right? And so take note what did I change. So one is work done on object, one is work done by object. What's the difference? Now work done on object means I'm giving the object something, so I'm giving you energy, right? So work done by object is what? It's like the object spend the energy on somewhere, probably friction on air resistance. Okay, so one is like giving you pocket money, right? Then the other, this is like giving you pocket money, and then this is like you spending away the pocket money, right? So it's kind of like a bit like accounting, right? All this money you have before, where did it end up at in eventually, right? So all this energy that you had before, where is the energy at the end? Because these two must be equal. If they are not equal, it means that so I think you all did the assumption paper, or I can't remember Heising, right? One of the question, right? They ask you calculate GP, then they ask you calculate KE. Then the next question asks why is it that the value is different? I think most of y'all will be able to answer that, right? So you are saying that that's because energy is dissipated. Yes, okay. Wasted into the environment, be it through sound, heat, light, etc. Okay. So following the law of conservation of energy, this must be true lah. Okay, and this is the main formula to use.
Sure,
Okay.
then how you find useful work done?
Okay, so haven't that one is under efficiency. So I finish power first. Okay, so at this point,
Sure, one more thing. When there's a slope and then you push the box up the slope, then the distance, is it the straight line or is it the distance of the slope?
you
Or is it like
okay? So the work done by you is along the slope because you are pushing the box along the slope.
okay.
Yeah. Okay, can, because we follow this rule, right? Must be in same direction as force, right? So your question you should phrase it in your head is how is the force of me acting on the box, right? So for those who actually don't know what Zhang is saying, so there's actually a slope, and then there's a box over here. So I exert this force F on this box, right? The distance that I want to calculate is this distance versus this distance, right? So this is wrong because D1 as opposed to D2 is actually in the same direction as F. So we want D1, okay? Whereas D2 is like not in the same direction, right? Because F is in this direction. Obviously, they are not in the same direction already. Can? 这样 okay
Yeah.
Okay. Anyone else got any question before I move on to power? Okay with energy. Okay, then let me move on to power, right? So power, just quickly mention it only, right? The SI unit is still watts. By the way, all these three are joules, because energy has the SI unit of joules, and what we are dealing with here is energy. Okay, so it's still joules. Okay, whereas power has the SI unit watts. I think most of y'all already know the formula for power, right? So in the previous chapter on DC circuit, we actually use power, and we use power equal energy over time in practical electricity to deduce our three other formulas, right? Which is VI, I square R, and V square over R. Okay, which I won't go through here. Yeah, so this power, right, goes to energy over time. This energy is the same as the energy I mentioned here, which means it's the same as this tree form. Okay, so whenever I talk about mechanical energy that you can see, right? The object is moving faster, you can see. The object is dropping, you can see. The object is slowing down because of friction, you can see. So we call this mechanical energy, right? So what we are dealing here with is actually mechanical energy, and it comes in three form. Ayo. Suddenly I forgot how to spell. Wait, okay, so yeah, okay, so mechanical, right? So what we are dealing here with here is called mechanical energy, and this mechanical energy comes in three form, right? KE, GP, or work done, either by object or on object, depending on the question itself. Okay, so don't be surprised if your E suddenly becomes work done. Then you're like, Is work done energy? Yes, work done is still energy, right? Because it's one of the three forms that we mentioned about, right? So power equals to energy over time, right? So this is the second formula of this chapter. Not really the second formula, but this is the power formula, which I think most of y'all will be able to remember already. Okay, so that's it for power. Now, then we go to the idea of efficiency, right? Because nothing in this world is actually 100% efficient, right? So efficiency is actually given by output of anything over input. So depending on what you want, how efficient is the power system? How efficient is the energy system? And then it will be output energy over input energy respectively. Okay, so this is the formula for efficiency. It's always out over in, right? Okay, yeah, it's always out over in, and yeah, I think yeah, that's how you calculate efficiency. Okay, so this is the idea of energy and power. Okay, if anyone has any question right now, please stop me, and then we can go through the idea of energy and power. Okay, I'm not going through questions because I think your papers have that, and because your paper have that, I think I'll just skip the question. Oh, yeah, I mean this is more like revision, not going through questions. Okay, Ken. So that's for pressure and energy power. So we have 2 chapters done. Okay, so the next part will be thermophysics, which is actually I need you to actually do some stuff for me. Okay, so first thing first is the kinetic model. Okay, so the kinetic model is pretty straightforward. I only need you to remember a few things. Okay, I think most of y'all should have the notes still. If you don't have, yeah, please go to the Google Drive that I shared with y'all. I think every note is there, right? The kinetic model note is quite straightforward. The main thing that you need to remember in this chapter is just solid, liquid, gas, and how they behave in different manner, right? So let me just draw a table for you. So there are 4 main categories to remember lah. Okay, and I won't really write out everything, okay, because I think this one is really pure memory work, and I don't think y'all need to memorize much. It's like I think y'all know already. It's like how to write. Okay, so here is the matter / characteristics, right? Then we have our solid, which is drawn in this manner, right? Fixed position, closely packed. Okay, 4 categories. Okay, then your notes may have more lah. Okay, but I memorize it with 4 categories only. Okay, then liquid is like not as closely packed, right? And then finally gas looks something like this. Yeah, and then the 4 categories, right? Yeah, I want you to remember Sam's father, right? So SAMF lah, right? So S stands for spacing, then A stands for arrangement, M stands for motion, and F stands for forces of attraction. Okay, so just remember Sam father lah. Okay, yeah, I think this is a good way to remember. Otherwise you may want to shift it around to get other acronyms. Yeah, okay, but I'll remember as Sam father. Okay, so spacing for solid, they are closely packed, right? For liquid, they are still packed, okay, with no empty spaces. So the spacing, right, actually gives us the idea of compressibility, right? Yeah, because the way solid is packed, they are so closely packed, and the way liquid is packed, they are packed with no empty space. Closely packed is quite obvious that there will be no empty space. Okay, the reason why we write for liquid packed with no empty space, right, is because they are not as closely packed as solid. Yeah, but we don't want people to think that just because they are not as closely packed, there's no empty space. All right, so these two actually gives us the idea why solid and liquid is incompressible, right? For gas, right, is like loosely packed, right? They are separated. They are not even packed really. right? So they are separated from each other. Okay, they are far from each other. Yeah. Okay, so far apart, right? Okay, so that actually, yeah, them being far apart, right, gives them a lot of empty space, and this empty space allows them to be compressed. Okay, so for the arrangement, these are in fixed position, these are in random position, and this is in random. Okay, then this one for motion, it vibrates, okay, about fixed position. Okay, this one is sliding past each other in random position. Right, so very common questions will ask you what happens as the object turns from a solid to a liquid. Of course, it's not so straightforward. They'll give you a graph, and then based on the temperature, they'll ask, describe what happens here, right? Then if you can identify, oh, that's melting, that's when solid becomes liquid. Then you can start to say that the object, the motion of the particles in the ice, right? They change from vibrating about fixed position to sliding past each other. Okay, and for gas, you can write at move at high speed. Okay, that's fine. Okay, gas do move at high speed. The air particles that are constantly hitting your face, right? I think they are moving at quite high speed lah. Can't remember. I think it's 100 plus meter per second. Okay, and that's actually quite high, right? Okay, so what is wrong is when students write higher speed. So cannot write higher speed. Okay, higher speed suggests, right, that it's suddenly moving at a higher temperature, right? Because higher speed means higher Ke, higher Ke means higher temperature. Okay, so out of nowhere, if let's say I ask you to describe how gas move, you suddenly tell me the gas move to the point where their temperature own self increase. That's a bit weird lah. Okay, so please take note that the motion of the gas, right, is that it moves at high speed and not higher speed. Okay, and of course in a random manner, right, because of their arrangement. Okay, in a continuous random. Okay, that means they are constantly moving and it's always random. Okay, the photon attraction, this is strong, this is okay, and then this is weak. Okay means it's not as strong as solid, but it's still strong. Okay, because the particles are still close together, right? So the forces of attraction, right, has to do with how close the particles are, right? So the closer they are, which is about spacing, then the stronger it is. Okay, so yeah, actually that's the idea of kinetic model, right? I think the notes have it in more detail about all these Sam father, right? So because this is quick revision, I'm just going to go through this part, and then I think we can move on to the next thermal physics chapter. So we are done with 6 and 7. We are also done with 8. So it's 9 and 10. Okay. So for chapter 9, right, it's actually thermal heat transfer. Okay. So for thermal heat transfer, there are 3 main methods, right? So chapter 9, heat transfer. There are only three main things you learn here. One is conduction, one is convection, and the other one is radiation. So as you actually learn in the next chapter, right, waves, right, next chapter, radiation, it works like waves, and waves, right, you can't actually see the wave itself. Yeah, you can't see it physically, right? It's not like when you're talking to someone. Okay, you can try. Yeah, you're muted, right? You just talk to the screen, right? It's not like suddenly you can see a sound wave coming out from your mouth. Yeah, but you know for sure that energy is being transmitted because you can hear yourself. And in fact, if you put your hand in front of your mouth, right, and just say a few things, right, you can actually feel the air pushing against your hand, right? And that's a form of energy, right? Because your voice actually projects out, it actually pushes the air, okay, and this actually gives the air particles kinetic energy, and it pushes to the point that you can actually feel vibration, okay, feel things coming out from your mouth, right? Okay, so clearly there's a form of energy, but you cannot see it. But that doesn't mean you cannot see it doesn't exist. Okay, you cannot see it can still exist. It's just you cannot see only, right? So the basis of conduction, it works through vibration, and the basis of convection, it works through density difference, right? And the basis of radiation, it works through waves, namely infrared radiation. Okay, I hope you all still remember a bit of your EM waves, right? So you have your gamma, your X-ray, your UV, your visible light, your infrared, your microwave, and your radio wave. Now we are talking about this, the infrared. Okay, so actually if you take an infrared thermometer near an oven, right? So when you stand near an oven, so I bake quite often. When you stand near an oven, you can actually feel like, wow, it's super warm. In fact, when I'm baking, right, my whole kitchen becomes very warm. Yeah. I don't think the whole convection current is set up in my kitchen, because even if the convection current is set up in my kitchen, right, my whole kitchen shouldn't feel so warm, right? Because hot air rises square sink, and then my ceiling quite high, so it should rise up all to the top. So I think what's making the kitchen warm, right, is the radiation through by the oven. So if we actually take a infrared camera and we take a photo of my kitchen when I'm baking, right, I think you will be able to see a lot of red color spots around my oven, suggesting that there's a lot of infrared around it. Yeah, and I think that's what makes my kitchen warm. Okay, so anyway, there's three main heat transfer. I think for this part, there are three animations that speak better than me. So we'll just take this time to watch three animation. Then I will explain quickly what is conduction, convection, and radiation, and the things to take note when we deal with this. And then yeah, and then we will be done with this chapter. Okay, so let's just pause here. Let me stop share. Okay, and then let me just find two videos. Okay, three videos, sorry.
Sure, I
Yeah.
want to ask,
Yes.
do you have to know the length of the wavelength of the EM waves?
There are some things you need to memorize, so later I'll tell you what to memorize. Can?
Yeah.
Okay, give me a minute. Okay, please let me know if you can't hear any sound from the video, okay?
So far, we've looked at conduction and convection, and both such methods use two particles to transfer.
Okay, wait. Okay, I'm gonna mute myself. Once I play the video, right, if within 5 seconds I don't hear anything, can start unmute and then just let me know. Okay, Ken? Thanks.
Conduction. So, here we see two young lads toasting some marshmallows on an open fire. One of them has chosen a metal rod to put their marshmallow on the end of, the other one chose a glass rod. Which one of them do you think is going to burn their hands on their rod first? Well, let's wait and see. Oh, there we go. We can see it was the guy with the metal rod. Why do you think that was? Well, actually, it's because metals are much better at conducting than glass. Glass still does conduct, just not as well. Let's zoom in and look at the particles in the glass and see how it conducts. So glass is a typical solid in the way it conducts. The particles by the fire start to gain heat from it and start to vibrate much more vigorously. They then collide with the particles next to them, passing on the energy, and slowly down the rows each particles vibrate more and more vigorously, passing on heat to the next one through collisions. So it progresses slowly through the glass. This is how conduction happens in most normal solids, and it's why solids are so good at conducting, because the particles are so close together that they collide very often. If you imagine it with a liquid or with a gas, the particles are quite far apart, so they do still conduct, they can still collide, it's just not going to happen very often. Right, now let's look at the metal and see why metals are such amazing conductors. If we look at the metal, we see there's still the same process happening as in the glass. The atoms near the fire gain heat and vibrating and colliding with the ones next to it. But there's an extra thing happening inside the metals. There's all these tiny little electrons whizzing around. They're called free delocalized electrons. They can bump into all the ions throughout the metal, so they can gain heat from the hot end and race straight down and bump into an atom at the cold end, therefore spreading the heat through the metal much, much quicker. This is why metals are so amazing at conducting. So, what's the key information to remember from this? Well, the key information to remember is that conduction is the transfer of heat via particles colliding with each other. Solids are the best at conducting because the particles are so close together. Liquids would be the next best, but they're pretty rubbish, and gases would be awful because the particles are so far apart they don't collide very often. Also, metals are the best of all solids at conducting because they've got free delocalized electrons, which can transfer heat from one end to the other very, very quickly. Conduct. End to the other.
Okay, so I think these are the 3 main points, right, to actually remember. Okay, so they transfer heat by colliding with each other. Okay, but do take note that for metals, right, they have this thing called the free delocalized electron, and we call them free electron diffusion. So through that process of free electron diffusion, they actually conduct heat faster, right? Because the electrons, they actually can transfer heat without colliding with, classically. That means they don't need to go bound by one by one. Electrons can cut through, yeah. Okay, so that's what electrons can do. So those coded part, right, electrons can just jump over there and just transfer the energy to that region, okay, which makes it very, very fast, right? So they are constantly cutting Q, right? And by cutting Q, they actually can transfer heat to the part where no heat is at yet. Okay, so that's how metals transfer heat, and then of course.
So for metals, I see there are free moving electrons present in the metal that allows heat to vibrate faster, or like...
No need. Just say that electrons are transferring heat. So later I'll teach you how to write, okay? So they will usually ask, right, why is a metal better conductor than say a glass? Yeah, so then you can say that while both transfer heat through collision of their particles, as the particles vibrate about their fixed position, they collide with one another. For metals, however, they have an additional process known as free electron diffusion, where electrons are able to transfer energy from one point to another without collision. So free electron diffusion is not about collision, okay? It's about the electrons going into a region where there's no heat energy yet. Yeah, that means that region is still not hot yet. Ken?
So what's the difference? Isn't it diffusion?
Diffusion and collision different, right? Diffusion is just going there. Collision means I need to bump into you, and then you bump into the person in front of you, then you bump into the person in front of you, then the energy flows from one dot to another dot, like that, slowly. So it needs to jump one by one, right? What if this region is hot and then this region is hot, but I want this region to be hot, right? Classically, that means insulator, they need to bump one by one. They need to bump one by one, like that, right? You see how long it took for my mouse to reach here, but for electron, you just need to do this.
Oh,
yeah. Can? So that's the idea of diffusion, right? I don't need to collide anything. I just jump here can already. Yeah, but this one, I still need to do this one by one. Yes, Asa?
You can see free moving electrons.
No. Oh, yes. Can. You mean to rather than free delocalized electron, is it?
Yeah.
In fact, you can just say free electrons can already.
Okay.
Yeah. Okay, Ken. So I'm just going to take a screenshot of this and paste it on our notes. Okay. Then later I will use it for. Okay. So let's move to the next one, which is convection. Right. So you can hear the video just now. No problem. should be okay. Yeah, okay. So let me just mute myself again. We'll watch the idea of convection. And then, yeah, later on we'll go back to our notes.
Convection. So, we've looked at conduction and we found that both liquids and gases are rubbish at it. But,
okay, by the way, they are rubbish because of their spacing, right? So, if it depends on collision, then the nearer you are, the better you are. Okay, that's why he says it's rubbish. Okay.
heat can transfer through them fairly easily, and the way it does this is by convection. Convection occurs only in fluids. Now by fluid, we just mean a liquid or a gas, something that can flow. And the way it happens is always the same. So, let's look at the gas particles in this room. They all have roughly the same energy, which we can see because they're all moving about the same speed. So let's put a fire in the room. Okay, now the particles by the fire start to gain energy from it, and they start to move faster. And because they move faster, they spread out. So that bit of fluid becomes less dense. And because it's less dense, it rises. Now, when those particles rise, they can't leave nothing behind, so the cool air or fluid moves in to replace them. But now this cooler fluid is by the fire, so these particles start to gain energy, and this bit of fluid then becomes less dense than the fluid above it, and it rises, pushing the other particles back round. These are now back by the fire, so guess what? They're going to gain energy. They're going to get even hotter, they're going to become even less dense, they're then going to rise. This is going to happen over and over again, forming a convection current. And that is how heat transfers through fluids, liquids and gases. So, what are the key points here? Well, the key points are that in convection, fluid near the heat source gains energy, becomes less dense and rises, being replaced by cooler fluid, which then in turn gains energy, becomes less dense and rises, forming a convection current, which then heats the fluid completely.
Okay, Ken. I don't think this is fully comprehensive because he actually never talked about how the fluid that is more dense, right, actually sinks. Right, so the convection current cannot be formed if only the hot air rises or the hot fluid rises. Okay, the cold fluid needs to sink. Then you get a cycle, right? Otherwise, if only the hot part rises, then you will only get half the cycle, and then the cycle will just stop there. Yeah, because if the hot fluid just keep rising and no cold fluid sinks, right? There'll be a traffic jam on top. Like it'll be too dense on top, right? Because if hot air just keep rising non-stop, so imagine it just keep going up, right, with nothing going down, so it just keep going up non-stop. So there will come a point, right, where the density at the top and the density at the bottom is the same, and then the whole convection cycle cannot work already. Okay, so this one yeah, it actually needs to talk about the colder part actually becomes more not becomes more dense. It's just that the hotter part is now less dense, right? So the bottom part, the cold part, right, it probably is as dense as before, right? But because of this, there's a density difference already. Hence, we say hot air rises coalescing due to density difference. Okay, and the difference is that hot air is always less dense than cold air, right? Because of the spacing, right? Okay. Yeah, give me a minute. Let me charge my tablet. Okay. So okay with convection. Okay. Let's move on to radiation, and then we'll go through my notes.
Hey, Jim.
Yep.
For convection current, it will stop at thermal equilibrium, right?
Yes.
Okay.
Okay.
For heat. So far, we've looked at conduction and convection, and both of these methods need particles to transfer heat. But heat manages to get to us from the sun, and there's definitely no particles in space. It's a vacuum. So, how does the heat from the sun get to us? Well, it travels as radiation, infrared radiation, or heat radiation to be precise. So, let's look more at this process of heat transfer of radiation. We actually find that different colours are better at emitting heat than others. Now, all hot objects emit heat radiation, and this is a physics term of hot. What it essentially means is any object above 0 degrees Kelvin or minus 273 degrees Celsius. That's what us physicists mean by hot. So anything above that emits heat. However, it will also be absorbing heat radiation. And it's only if it's hotter than surroundings that it's actually going to be emitting heat overall. So let's add some boiling water to this cube to make it hotter than the surroundings. And let's see what happens. First, let's look at the shiny silvery side. We can see that's really rubbish at emitting radiation. There's hardly any waves coming out of there at all. If we then turn to the white shiny side, we see that's only marginally better, still pretty rubbish at emitting radiation. The matte white side, slightly better, but still pretty rubbish. Let's go round to the shiny black side, and we see all of a sudden that is emitting a fair bit of heat now. But now if we turn around again and we see the matte black side, we can see that is going like crazy. That is emitting loads of heat radiation. And we can see from this that matte black is the best colour at emitting heat radiation. So, what colours can be best at absorbing heat radiation? We've seen that matte black is definitely the best emitter, but what colours can be the best absorber? So there's a really easy experiment for this. We have a nice heat source in the form of a fire, and we can stick, using just some wax, 2 marbles onto a couple of plates. One plate with a shiny surface, and one plate with a matte black surface. So, whichever surface absorbs the most heat radiation is going to melt the wax the fastest, and therefore the marble will drop quickest. So which one do you think it would be? Well, let's look and see what happens. Well, first off, I can notice that the shiny silvery surface is reflecting away all of the radiation. The matte black surface is the
not all, most, okay? Not all.
The matte black surface is absorbing all that heat.
So here, not all, okay? It's most, alright? That's why it still gets hot eventually.
Radiation, all that radiation. So I'm going on the, there we go. The matte black fell off way in advance of the shiny silvery one. The shiny silvery one's still pretty stuck on there. And we can see why. It's because matte black is absorbing all that radiation, shiny silvery is reflecting it. So what's the key information for us to have here? Well, when heat needs to transfer across a vacuum, the only way it can do it is by radiation. We've also seen that matte black is the best absorber and emitter of radiation. And that's why if you want something to heat up really, really quickly, or something to cool down really, really quickly, we colour it matte black. We also saw that shiny silvery surfaces were the worst at both absorbing and emitting radiation, and that's why if we want something to stay hot, or if we want something to stay cold, we use a shiny silvery surface.
Okay, Ken? Okay, so just quickly, right? So say matte black is the best absorber, shiny silver is the worst in absorbing, right? So it's the worst, yeah, okay, it's the worst emitter or the worst absorber, right? Okay, so these two are just nice, right? Your iPhone color, right? Also got matte black and shiny silver. Okay, so if let's say it probably does, right? Okay, so if let's say the iPhone casing, right, the iPhone color that you choose, whatever color outside is also the same color inside, right? I got a feeling it probably is, yeah. So which one should you choose? Should you choose matte black or shiny silver?
Black.
Black, why?
Because it's a better option.
Better what?
It absorbs heat.
But why you want the phone to absorb the heat? Okay, so then the question you should ask yourself, right, is which is usually hotter, your phone or the environment?
Phone lah.
Phone, right? Okay, because if you are using a phone, it's constantly hot right? So your phone will be hot most of the time. Now, matte black is the best absorber and emitter, right? So if your phone is usually hot, so heat will transfer from your phone to the surrounding, right? And you want it to transfer as fast as possible. You want it to transfer out as fast as possible. You want your phone to stay cold. You don't need to stay too hot, right? So actually, in that case, you actually want a black phone because it's the best emitter. Okay, so I'm banging on the fact that black is a good emitter, and therefore we use a black phone because it can emit heat out faster. Okay, that said, I think the casing behind is actually metal, so I think it's a metal with some silicone, or I don't know. I actually don't know what material they use. Okay, so any case, the matte black and shiny silver iPhone colors, right? Okay, I think it's quite clear cut that you want matte black because of the emission property. Okay, so we actually go back to my notes again.
Wait, sorry.
Yes.
So shiny silver will keep its temperature in a way like it will not lose or gain much, is it?
Yes, correct. So if let's say your phone very hot already, right, needs to like let go of the heat, right? But it's shiny silver, the heat cannot come out, and that might cause a problem for your phone now. Okay, can I, Robin?
Yes.
Okay. So yeah, let's talk about these three quickly, and then we'll move on. The basis of all these three, right, is the idea of heat transfer, because this is they are just methods of heat transfer. But other than methods, right, the principle of heat transfer is that heat transfers always occur from higher temperature to lower temperature. Okay, sorry, always occur from a region of higher temperature to a region of lower temperature. Yeah, maybe I just add for you, right? Okay, so a very classic. Okay, so now you all have a understanding of conduction, convection, and radiation, right? Okay, later I'll send you all the 3 videos, the link to these 3 videos alongside with these entire notes. Okay, so I'll just put a space here. I'll just add QR code and links to these 3 space. Okay, so that you can actually access the video anytime you want, right? Okay. Yeah, so I think roughly you know conduction. The thing to remember about conduction, okay, is that there's collision. Okay, so so it works in any medium. It's just that how close and packed the medium is, right? And then for metals, there's this idea of free electron diffusion, which makes them conductors. Okay. Then there's convection, which really works by density difference. So temperature difference causes density difference. Okay, this density difference causes hot fluid to sink. To rise, sorry, and cold fluid to sink. And this entire rising and sinking, so hot and cold. Okay, so must talk about density difference every time you talk about convection. Okay, so this hot fluid rising and cold fluid sinking creates a convection current. Okay, so this convection current is this thing over here. Alright, and lastly, radiation is just heat transferred through waves, namely the IR radiation, right? Infrared radiation, right? This one works in vacuum because obviously waves can pass through vacuum, right? Waves don't need any particle to pass through. This is not a sound wave, okay? Sound wave would need particles, but this is a EM wave. Okay, so this is EM wave. EM wave is like light like that. Okay, so if you can see sunlight, right, then this will be fine. Okay, so that's the basis of this tree of just a quick summary on how it actually works. Okay, any question regarding this tree? Oh, and of course the property of radiation, this one must remember, okay? Black dull versus silver shiny or white shiny. Can? Yeah, hope I didn't miss out anything. Okay, so I just paste the 3 QR code, and then I think let me just get an image. I think a very popular question is your thermal flask, right? So let me just take a photo of a thermal flask, and then I'll paste it here. Then we can quickly. I think if you all did the, I can't remember again. One of the paper, either Heising or Assumption, you all have come across this thermal flask thing. So let me just get an image. See here. Okay, so over here we have a vacuum flask diagram. Okay, so it's quite pixelated. Okay, but I think we can make do. Right, so first thing first, over here there's an insulated support. Right, so this insulated support is with regards to conduction. Right, so because it's insulated, it slows down the rate of heat flow. Right, this vacuum here is also about conduction, right? Because heat will want to transfer out this way, right? So if it's not vacuum, heat will be able to transfer like this through conduction, okay? And then the outer surface will be hot. And then when the outer surface is hot, that means the warm water has already loose heat to the bottle. So usually when you hold thermal flask, the outside, right, is quite cooling one because conduction has not occurred yet because of the layer of vacuum. Okay, yeah. So this is your hot liquid or your cold liquid. The double wall, right, probably traps air, which is another layer of insulator. So there's a lot of mechanism to actually prevent conduction from happening. So you can see, right, whenever two objects are in contact, namely the water and the entire bottle, right, they are in contact, conduction will occur most definitely. So we need to come up with a lot of ways, right, to slow down conduction. Okay, and these are the ways to slow down conduction. Now, if this entire bottle is vacuum, right, then there's no supporting structure at the bottom. This bottle may become very flimsy. Okay, might spoil quite easily. That's why over here there must be a support. But because there must be a support, and we want to slow down conduction, it needs to be an insulated support. So eventually, your thermal flask, right, can become warm, and that's why it's important that over here, right, a good design, this probably a more expensive thermal flask, will have a double wall container. So the double wall container traps air in between the two layers, and air is another layer of insulator. So over here, the conduction will occur, but occur through a insulated support. Then, as the insulated support tries to transfer heat to the environment, it needs to go through another layer of insulator. Even though it's metal container, in between the two metal container is air, and air is an insulator. Okay, so all these are for conduction. Okay, so I'm just going to write here conduction. Okay, not really going to write out the answer, right? And then over here we have silvered surface. Silvered surface, if you see the word silver or black, right, you need to know that it is about radiation. Yeah, okay. So poor emitter and absorber of heat, right? So if it's hot, then it won't be able to emit heat as fast. The heat will be trapped inside. Okay. Lastly, right, the cork or the stopper over here is for convection. So why is it for convection? It's because as the hot air rises, it is unable to escape, right? So because it's unable to escape, it cannot form convection current with the surrounding air. Now what happens if there's no stopper? Then the hot air rises, while the cold air outside will sink in. Okay, then as the cold air sinks in, right, the water will start to lose heat to the cold air. Then the cold air will become hot, then it will rise up again. Then what happens is it rises up, another cold air comes in. So the cold air keeps coming into the water to take heat away from the water. Okay, but by having a stopper, okay, just by having a stopper, we are going to prevent this from happening. So the hot air will be stuck here, right? Eventually, at most, all the air here is warm only. Yeah, that's it. Okay, so you are just warming this portion of air. So it's fine even if there's a convection current, but the convection current is within the water itself. Okay, what is not fine is that the convection current starts to go out of the water, so it exchange heat with the surrounding air. Okay, so this one quite important, the phrasing I'll write for you. So exchange prevents exchange of heat with surrounding air. Yeah, okay, so the thermal flask design, right, is actually very smart, right, because it actually compromises of all these three elements: conduction, convection, and radiation, into like one thing that we most often use, which is the vacuum flask. Okay, I think at least teachers do use that quite often. Okay, because I think everyone drinks coffee in the staff room almost. Yep. Okay, so this is the idea of transfer of thermal energy. And then we're just left with the last one, thermal properties of matter. Okay, which is your cooling curve, your evaporation, etc. Okay, after this we'll take a short 10 minutes break before we go back to waves. Okay, so far everyone okay? Or do you need a break now? Anyone need a break now?
Yes.
Or need a break? Okay, then maybe you take a yep, it's recorded. Then maybe you take a 5-10 minutes break. Can everyone be back by 12? Okay, let's just or rather, can everyone be back by 11:55? Okay, so we'll just take a break, be back by 11:55, and then yeah, we got how many more chapters to go? Be back by 11:55, then we got 5 more chapters to go. Okay, for waves I'll go through faster, yeah, except light now. Okay, okay, so 11:55, see you later.